Let us examine the potential energy of a point-like body under the influence of a conservative force. We saw that the work W done on a point mass by the conservative force F along a curve C between 2 points A and B depends only on these points. In other words, the work W is a unique function of the points A and B, and it is independent of the curve C connecting the 2 points. Let us choose a point P0 such that the curve C does not pass through it. Then the points P0 and A can be connected with an arbitrary curve C1, and the points P0 and B can be connected with another curve C2. Now we can talk about the work which the force F would do if it was exerted on the point mass along the curve C1 or the curve C2. Since the force F is conservative, the work done by the force F along the curve C1 between the points A and P0 is a unique function of the initial and the final points of the curve. Similarly, the work done by the force F along the curve C2 between the points P0 and B is also a unique function of the initial and the final points of the curve. We can consider the work done along the union of the curves C1 and C2 connecting the points A and B as well, which must be the sum of the individual works done along these curves. Then the sum of these works depends only on the points A and B, and it is equal to the work W done by the conservative force F along the curve C between the points A and B. Here the point P0 is an arbitrary point. However, if we fix this point called 0 point, only the points A and B are needed to determine the works done along the curve C1 and C2. If we introduce a 0 point for the conservative force F, then the potential energy of a body at a given point can be measured by the work done on the body by the force when it is brought from the given point into the 0 point. As a result, the potential energy of the point mass at the point A is given by the work done on the point mass while it is brought from the point A into the point P0. The work is equal to minus the work done on the point mass while it is brought from the point P0 to the point A, which is given by minus the line integral of the force F with respect to the arc length along an arbitrary curve connecting the points P0 and A. Obviously, the integral vanishes if the 0 point P0 and the point A are the same, that is the potential energy of the point mass is 0 at the 0 point. Now we can state that a point mass under the influence of a conservative force F has the potential energy at a given point P, which is equal to minus the line integral of the force F with respect to the arc length S along an arbitrary curve connecting the points P0 and P. Here the potential energy is defined with respect to the 0 point P0. We have seen that the work W done on a point mass by the conservative force F along the curve C between the points A and B is equal to the sum of the works done along the curve C1 and C2 connecting the points A and B through the 0 point P0. Here the work done along the curve C1 between the point A and the 0 point P0 defines the potential energy of the point mass at the point A. Since the work done along the curve C2 between the 0 point P0 and the point B is equal to minus the work done in the opposite direction, we can express it as minus the potential energy of the point mass at the point B. As a result, the work W can be written as the potential energy of the point mass at the point A, minus its potential energy at the point B. Then we can state that the work W done on the point mass along an arbitrary curve between the points A and B is given by minus the difference in the potential energy of the point mass measured at the points B and A. In other words, the work done on a point mass by a conservative force is equal to the negative change in the potential energy of the point mass. If the force F is the net force acting on a point-like body, then we can apply the work-energy theorem stating that the change in the kinetic energy of the body between the 2 points A and B is equal to the work done on the body by the force along any path between the 2 points. By substituting the result derived above into the theorem, we can see that the change in the kinetic energy of the point mass is equal to the negative change in its potential energy. After regrouping the terms in the equation, we obtain the law of conservation of mechanical energy. When we proved the work-energy theorem, we did not assume that the force changing the state of the motion of a point-like body is a conservative force. In the computation of the work done by the force, it does not matter whether the line integral of the force with respect to the arc length along a curve depends on the curve or not. Therefore the theorem holds for both conservative forces and non-conservative ones, if they are applied on the point mass. However, the law of conservation of mechanical energy is formulated for such processes where a conservative force is exerted on a point-like body or system of bodies. The generalization of such a law for both conservative and non-conservative forces involves all possible forms of energy, where we can talk about the law of conservation of energy, that is the total energy of a body or a system of bodies. The total energy of a body or a system consists of all forms of energy which are related to all types of forces acting on the body or the system. These forces can be conservative forces such as gravitational, elastic or electrostatic force, and non-conservative forces such as frictional or drag force. In the examples illustrating the energy defined for different phenomena, we will present bodies accelerated by either a conservative force or a non-conservative one. Since we focus on conservative forces, we study the conservative force F acting on a point-like body in the general case, where the force depends on the instantaneous position of the body. Then the force F can be described by a vector function of the position vector r of the point mass with respect to some reference point O representing a frame of reference. It is normally convenient to choose the reference point O as the 0 point P0 for the definition of the potential energy of any point mass accelerated by the force F. The definition of potential energy also shows that the conservative force F determines the potential energy and vice versa. By definition, the line integral of the conservative force F along an arbitrary curve depends only on the endpoints of the integration, and the line integral along a closed curve vanishes identically. In other words, the line integral of the force F with respect to the arc length s along an arbitrary closed curve C0 is equal to 0. Here we can apply Stokes' theorem stating that the line integral of the vector f along the closed curve C0 is given by the surface integral of its curl, that is the cross product of the nabla operator and the vector f over an arbitrary surface S, where the curve C0 is the boundary of the surface. Since this surface integral is identically 0 for the conservative force F and the surface A is arbitrary, the integrand must vanish. That is, the curl of the force F is identically 0. By applying a vector identity stating that the curl of the gradient of any scalar function f vanishes, we can assume that the conservative force F can be written as the gradient of some scalar function f depending on the position vector r. In fact, we can demonstrate that the function f is determined by the potential energy of any point mass moving under the influence of the force F. We define the potential energy of a point-like body accelerated by the force F at the point P by minus the line integral of the force F with respect to the arc length s along an arbitrary curve between the 0 point P0 and the point P. Since the force F is conservative, we can write it as the gradient of the function F. Now we can apply the fundamental theorem of calculus, which gives minus the difference between the function F evaluated at the points P and P0. If the 0 point P0 is fixed, then we obtain minus the function F at the point P plus a constant. As a result, the potential energy of an arbitrary body at the point P is equal to minus the function F plus a constant, where the constant represents the free choice of the 0 point in the definition of potential energy. Then we can conclude that a conservative force F is given by the negative gradient of the potential energy of any point mass moving under the influence of the force. If we attach a Cartesian coordinate system to the frame of reference, the Cartesian components of the force F are equal to minus the partial derivatives of the potential energy with respect to the corresponding coordinates. Conversely, if there exists a scalar function such that the force F is given by the negative gradient of the function, then the force F is conservative, and the function represents the potential energy of an arbitrary point-like body accelerated by the force. Based on this criterion, we can immediately determine whether gravitational force is conservative or not. We already computed the potential energy of a body of mass m at the height h, which is equal to the mass m times the magnitude of the gravitational acceleration g times the height h. If we choose a Cartesian coordinate system with its origin at ground and the z-axis pointing upward, we can write the height h as the z-coordinate of the body's position. We obtain the components of the force F by computing minus the gradient the potential energy of the body, that is its partial derivatives with respect to the corresponding coordinates. Then the force vector has the component 0, 0 and minus m times g. That is, the force F exerted on the body is equal to its mass m times the gravitational acceleration g pointing downward, which is the gravitational force acting on the body. As a result, we demonstrated that the gravity is a conservative force. Of course, this fact is already known for us because we introduced the concept of conservative force based the example of gravity. However, in that case we determined if the force is conservative by checking if the line integral of the gravitational force along a curve depends on the curve. Here we go in the opposite direction. Instead of integrating the force exerted on the body, we compute the gradient of the potential energy of the body to obtain the conservative force acting on it. We can also determine whether the elastic force produced by a spring is conservative or not. We already saw that the potential energy of a spring stretched by an amount of x0 from its equilibrium length is equal to 1 over 2 times the spring constant k times the square of the displacement x0. Let us suppose that the x-axis points in the direction of the displacement and the x-coordinate represents the displacement x0. Then the components of the force F given by minus the partial derivatives of the potential energy with respect to the corresponding coordinates are equal to minus k times x, 0, 0. As a result, the force F is equal to minus the spring constant k times the displacement vector x, which is Hooke's law showing that the elastic force produced by the spring is a conservative force. Both examples illustrate that the energy of a body depends on the choice of the 0 point or the reference state of the body, and different choices result in different values of the energy for a given state. In the case of a point-like body under the influence of gravity, the local definition of its potential energy uses the state of the body at rest on the ground as a reference state A0. If we choose the state of a point mass m at sea level as a reference state, we have a global definition of the potential energy. Then the height h is equal to 0 for a body in the reference state. For a local definition, the potential energy of the point mass at the height h, that is in the state A, is given by m times s times h, minus m times g times h0, where h0 is equal to an arbitrary altitude chosen as reference state. Similarly, if the reference state A0 of a spring is not its equilibrium state but the state in which it is slightly stretched, then the potential energy of the spring stretched by an amount of x0 from its equilibrium length, that is in the state A, is equal to 1 over k times x0 squared, minus 1 over 2 times k times x0 bar squared. Here x0 bar gives the difference between the length of the relaxed spring and the length of the slightly stretched one. Such a choice of the reference state can be done in the case of kinetic energy of a body of mass m at the speed v as well, which is equal to 1 over 2 times m times v squared. If the reference state A0 of a body accelerated by a force is not the state when it is at rest but when it has the velocity v0, then the kinetic energy of the body in the state A is given by 1 over 2 times m times v squared, minus 1 over 2 times m times v0 squared. The fact that the energy of a body or a system of bodies is only defined to within an additive constant due to the arbitrary choice of the 0 point of the energy, has no physical significance. Since only the differences of the same form of energy appear in the work-energy theorem and the law of conservation of energy, the additive constants depending on the choice of reference states cancel out.